Welcome to AP Podcast 15.6. This is on Solubility Equilibrium. And for the most part, all it is will it all dissolve? And if not, how much? Now, when you're dissolving stuff, imagine sugar, salt, and water, it dissolves pretty easily. Well, it turns out a lot of things dissolve, but not necessarily do they dissolve completely. So there's a couple things that are really important. First of all dissolving is an equilibrium. All right. So you might get a little dissolving. You might get, for example, if you think back to solubility rules, we would say something like silver chloride is insoluble in water. Well, that's true, but to a point, silver chloride dissolves a little bit in water. Think about our sulfate rules. We know that lead sulfate is insoluble. Well, lead sulfate will dissolve a little bit in water. Now, what about sodium chloride? Well, you know that any element, or probably any solution with an alkali metal dissolves really easily. But I can tell you from mixing solutions, not all powders that I have that have group 1 metals dissolve as easily as something like table salt. So anyways, that's kind of what we're looking at here. And what we're going to do is we're going to look at the idea of this equilibrium. And as you add more solid, the solution gets more and more saturated. If you've ever made rock candy, you're dumping in sugar, stir, 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 heating it up until all of it will dissolve. So if you think about the equilibrium here we have the solid, and then we have the dissolved portion. Now I'm dumping in sugar and dumping in sugar and dumping in sugar or whatever ionic compound, and eventually, as I'm dumping in, the stuff that I'm dumping is dissolving, but the solid precipitates out as fast as it dissolves. So we get to that point where, from the naked eye, from our view, as I'm dumping stuff in, the stuff in solution is precipitating out. Okay? And when you get to that point, you have a solution that is saturated. Now, what do we do with chemistry and this stuff? Well, guess what? We're going to have ourselves another K, another equilibrium constant. This is the solubility product, KSP. And like all equilibrium constants, when we write them out, okay, we write the products over the top of the reactants. But look at this reactant. This reactant is always going to be the same. It's always going to be a solid. And you guys know that we don't put solids, liquids, or liquids in our equilibrium expression. So this is always going to be the same thing. KSP equals the cation times the anion. Now, what's different is, think about when we're talking about acid dissociation, right? Okay, H plus and A minus, right? And whenever we were solving for X, we were always solving with an X squared on top. Well, that's going to change here, because we're going to have coefficients here, which we did not have acids and bases, and we got to remember to put them up there, just like we did when we were calculating the equilibrium. So that's something that caused some kids some problems, but we're going to try and make sure we don't have that happen. So let's just basically start out at an easy point here. Write a balanced equation and the solubility expression for the following. All right, I'm going to do the first one. Okay, Ag2CO3. So basically, that equation would look like this: Ag2CO3. And what does that break up into? It breaks up into 2 silver ions, right, and 1 carbonate ion. Now, if I'm going to write out the KSP for that, that equals Ag plus squared, right, times the concentration of CO3. All right, and notice there's nothing underneath, because this is a solid. Super important. All right, so you can imagine doing the same thing with the other three. We're going to move on because it's a pretty trivial thing. So let's look at the next thing. A couple things I want you to really focus on. The title of my slide, I was being clever here, right? Watch out, because solubility is not the same as solubility product. Now, solubility product is when you multiply two things together, right? In other words, a positive ion, the concentration of a positive ion times the concentration of a negative ion. That's a solubility product. But solubility is how much is going to be dissolving. And so when we use these terms, solubility product, or I'll usually say equilibrium constant, or solubility, you got to keep those two straight. And so like all like all equilibrium constants, the solubility product is not going to change except with temperature, right? Temperature changes, it'll change. And you can think about that. I mean, if you're dissolving some stuff in water, some ionic solid, most of them will dissolve more in warmer water. Not all, but most of them will. Okay? But as far as solubility, that's just how much stuff can dissolve. And we're gonna calculate both. Now, this last thing, a common ion can change us. We did a little bit with a common ion with acids and bases, and so we want to make sure that we're aware of that, and we'll spend some time with common ions. So let's get to calculating real quick. All right, here's a couple problems. Find the KSP of the following. And so we're going to find the equilibrium constant for the solubility of copper bromide, right? Now, to help myself out, just to keep track, I'm just going to write this out. CuBr breaks up into Cu plus and Br minus, right? All right, so my KSP equals the concentration of Cu plus times the concentration of Br minus. And since I only have one of each, I don't have to put any kind of exponent up there, right? Now they've given me the solubility in moles per liter, right? And moles per liter is, of course, concentration. So basically I'm going to take 2.0 times 10 to the minus fourth and times it by 2.0 times 10 to the minus fourth. And I'm going to get an answer of 4.0 times 10 to the minus 8th. Okay, so I've just calculated the KSP for that. All right, not too bad. Now, take a moment, pause the video, see if you can do the next one, and then be aware of the formula. All right, did you get a value that is 1.1 times 10 to the minus 73? Boy, what a ridiculous number. What does that basically tell you? That basically tells you can't dissolve any of this stuff in water. Now, if you didn't, let's look at a couple things. Did you think about what this is going to break up into? Okay, if I just write out the reaction, Bi2S3, it's going to break up into 2 bismuth, 3 plus ions, and 3 sulfide ions, right? Because that's going to play a role. So if I write out the reaction, KSP equals bismuth 3 plus squared and sulfide cubed, right? However, here's something that's super important. Notice these are concentrations, right? Did you plug this number in, 1.0 times 10 to the minus 15th, into here? Because if you did, you made a mistake. Because of what? The mole ratio. This is where KSP is different from our acid-base stuff and where you got to really, really pay attention. So your number should have been 2 times this number, right? For every one of those, I'm going to need 2. Don't forget the mole ratio. So this would be 2.0 times 10 to the minus 15th times, and then this is 3, right? This ratio is 3 to 1, 3.0 times 10 to the minus 15th, right? And that's where you get this big number, pardon me, this little number with a giant negative exponent, okay? And so I've got this quote from one of the greatest movies of all time, The Princess Bride, and Vizzini talks about making a classic blunder when he's in a battle to the death with Wesley. But what I want to talk about is the third rule is always pay attention to mole ratios. Okay? Cannot tell you how many times students forget this thing right here. All right? Don't forget that mole ratio. All right? If you do that, these problems are easy. If you don't, they're completely tough and you get them wrong. All right? On to the last slide, calculating solubility. Now imagine that they've given us the KSP, but what they would like us to find is the solubility of the salt. And so we want the solubility of the whole thing. So what am I going to do? I'm going to write out Cu, and I know this is kind of a trivial thing for some of you, okay, but it's good practice. That's a copper 2 plus and 2 iodates, all right? It's just good practice to do this. All right, so I've got that. And then I'm going to write out my expression, KSP equals concentration of Cu and the concentration of iO3 squared, right? Now, I've got a value for KSP. It's 1.4 times 10 to the minus 7th. And then I'm going to solve for X, right? Well, X is no problem for this one, for copper, because it's a 1-to-1 ratio of this to this, right? So that's just X right there. But what's this? Look at that. There's 2X in there because of this mole ratio, right? So it's 2X squared. All right? So then when I do my amazing math, I get 4X cubed equals that. And without using a calculator, I'm just going to look at my notes. The answer I get is 3.3 times 10 to the negative 3 moles per liter. Now, check with your calculator to make sure you solve for X correctly. Now, what does that mean? That means that copper 2 iodate will start precipitating when the concentration is that low. Or another way to look at it is that much will dissolve before it starts precipitating out. Okay, so there's solubility, and we'll practice a number of these problems, and we will see you next time.